Now, students, I hope everybody is fine. And and in today's topic, we will be discussing operators. I'm talking about operators in quantum mechanics. The mechanics that's based on the presumptions of de Broglie matter waves that has the basic mathematical equation as Schrodinger's wave equation, and and the point is that how can we define these operators and what are basically operators, and these operators. An operator is basically, I should call it a rule. It's a rule by means of which a given function is changed to into another function. So this is what an operator does. It operates and and you are able to get another function out of it. To be very trivial in sense at this point of time. So so in quantum mechanics, what we have what we call as observables. Observables. What are observables? These are basically the measurable quantities. Observables. What are they? These are measurable quantities. The quantities that can be measured. And the examples of these observables are, say, energy is an example, momentum is another example, position is another example, etc. So anything that can be measured, we call that thing as observable, and we have we have the observable quantities in quantum mechanics, and the examples of these observable quantities are like this. Now, each of these observable quantities, I mean, each of these observables or measurable quantities has a definite operator associated with it. It has a definite operator associated with it. So if I have energy, I have if energy is an observable, that means it has an operator associated with it. If I have momentum as an observable, it has its associated operator, and the same thing is for position and the other things that can be measured that act as observables. They definitely have an operator in quantum mechanics. Now, to move on from here, if I take an example of Schrodinger's wave equation and Schrodinger's wave equation, and I can write down this H psi is equal to E psi. Now, this H refers to the Hamiltonian, and this E refers to the energy. In actual sense, we call it energy eigenvalue. Now, the point is that with this Hamiltonian, we have an operator associated with it, and we have the operator associated with the energy. Now we can see if we go back to this Schrodinger's equation, we have the Hamiltonian operator, and we have energy operator. So to move on from here, now if I have to write the operator for Hamiltonian, say for example, I will choose that as H cap. The operator for Hamiltonian would be Yeah. For that, better is to write down the Schrodinger's equation in terms of this in terms of these operators. So what we have the Schrodinger's equation, and what's that? That is minus h bar square by 2m. Then we have del square plus v of psi is equal to I h cross del by del t of psi. That should be clear. So this is basically h psi is equal to E psi. Now here what I have an operator associated with an observable, and the operator for Hamiltonian, if I talk about operator for Hamiltonian, and this part is time independent, so we are taking the time independent part of Schrodinger's equation. So if I have h cap as an Hamiltonian operator, this will be minus h bar square by 2m del square plus v. So this equation is a representation of Hamiltonian operator for time independent part of this equation. And if I have to write down the Hamiltonian for time dependent, so Hamiltonian operator for time dependent Schrodinger's equation. So what is that? That's going to be E cap is, or you can call it energy operator, and that's going to be I h cross dou by dou t. So to every observable in quantum mechanics, we have a corresponding operator. So we have an operator for Hamiltonian for the time independent part of the Schrodinger's equation, and we have the Hamiltonian operator for the time dependent Schrodinger's equation. Now to move on from here, let us have the operators for momentum. So let us have the operators for momentum. So momentum operators. Okay, so what is Hamiltonian? It's basically the sum of kinetic energy and the potential energy, right? So this is the Hamiltonian that we have, and if I write the observable for the kinetic energy, that's p squared by 2m plus v, and that should be clear. Now the point here is that from this equation I can have an operator for kinetic energy, and I can also have an operator for momentum, right? So if I have to write down the corresponding operator for kinetic energy, so if I represent k cap, if I represent k cap as the kinetic energy operator, so what is the replica for this in Schrodinger's time independent part? That is basically okay, if I write down this p squared by 2m here, but for the operator for kinetic energy to be an operator, what I have here is this minus h cross square by 2m del square. So minus h cross square by 2m del square. This is the operator for kinetic energy. This is the operator for kinetic energy, that's minus h cross square by 2m del square. And that should be clear. So here, what we have is an operator. Now, what is an operator? An operator is basically a rule by virtue of which a given function can be changed into another function. So that's what this operator means. So if I have this as the kinetic energy operator, what will be the operator for momentum square? Yeah. So if I go on from here, so operator for momentum square. All right. So what should be that? In that case, this operator for momentum square should be, yeah, it should be, come on, the 2m part will be multiplied here. So this will be 2m times minus h bar square by 2m del square. So this 2m and 2m will go. So for momentum, I have momentum square operator is basically minus h bar square del square. That's the case. Now, if this, if we resolve this, if we write down the components of this momentum at this point, we can have the square of momentum operator along x. The square of momentum operator along x will be minus h cross square dou 2 by dou x2. And along y, the operator will be minus h bar square dou 2 by dou y2. And for pz, operator along z will be minus h bar square dou 2 by dou z2. So this is how we can have the square of momentum operator represented in terms of the partial derivatives of the components that we are linking to the particular momentum operator square. So from here, if we move from here, we can have the momentum operator. So we can have the momentum operator as it will be minus h bar and del. So this will be my what I call as momentum operator, and this momentum operator I can write as I can use h bar by I for it and del. So from here we have we can basically represent this equation by where is the original equation? That is P operator square minus h, is equal to minus h cross square then del square. It's minus, right? So I can think of using P square as h cross square divided by iota square del square. I can think of using it like this because iota square is going to give me minus 1. So this is plus here. So if this is plus, now if you will be rooting on both sides to this equation, you will have the momentum operator. So in that case, the square and root will cancel with respect to iota, and you will have iota here in the denominator. So that's why we have the momentum operator as h cross by I del. Now, this momentum operator can be written in terms of its components. We can write down it in terms of x, y, and z. So if we do that for px, what we will have is h cross by I, it will be dou by dou x. And similarly, px will be h cross by I, dou by dou y. So similarly, we will have pz, that will be h cross by I, dou by dou z. So these will be corresponding momentum operators along x, along y, and along z. And and if we go back to kinetic energy operator we had somewhere, and we can obtain from that equation, we can obtain this. Where is that? We can obtain the operator for velocity. So if we directly go back uh, to to kinetic energy, so this is my 6. Okay, now if I go back to the kinetic energy operator, what was that? That was h cross square by 2m del square, and that too it was minus, right? So this is our kinetic energy operator, and I would like to have velocity operator from this equation, and I can have that by simply thinking in terms of kinetic energy, and what I have in that case is 1/2 of mv square. Now for V as an operator, I will use V cap. So is equal to uh, this is equal to minus h cross square by 2m, and then we have del square. That's the case. Okay, so this m can come here. This 2 and 2 numeral can be got rid of. So velocity operator square it's basically minus h cross square. So this m and m will go as m square. So this minus I can write uh, as I did previously. For this minus I can write h cross square by iota square m square and then del square. This is how I can treat it. So what am I going to get? So this minus will not exist, it will become plus. Once you have the value of iota square, you will have -1. So what will be the operator corresponding to the velocity will be h cross by iota del square, del. So you can write down the operators for velocity components like Vx cap and Vy cap and Vz cap. And say if I have to write it for Vx cap, I'm going to write h cross by I cap dou by dou x. So this is going to give me the operator for, I have missed m here, sorry. This is m, okay? This is m. So this is going to give me the operator for velocity. So for velocity, I have a corresponding operator, and what's called as velocity operator. And this velocity operator is h cross by I m del. And if we move on, similarly for potential energy, we must have an operator. So for potential energy, we have a corresponding operator. So I have a physical quantity V, and its corresponding operator can be written as V cap, and we can have operator for position. So for position we can have an operator. Suppose I have R as a position, so its operator will be R cap. So accordingly, this is how the operators are or developed, and these operators play a very key role in achieving, in getting the information from the wave function. So if I would like to have some summarization of these operators. I think there is no need of having any summarization, but still I can try for some little bit. Say for example, if I talk about energy, okay, and in terms of energy, I have two operators. One is in terms of time. One we have is the time independent operator. And what is that? That is minus h cross square by 2m del square plus v. And we have time dependent operator. We have time dependent operator, and that time dependent operator is I h cross dou by dou t. And similarly we have, if I move on from here, as in order to try to summarize this thing. So similarly, if I have kinetic energy, so for kinetic energy, I have a corresponding operator, k cap, maybe the symbol, and the operator is minus h cross square del square by 2m. So this is what is evaluated, and then what we have is we have momentum operator. So for momentum, we have p cap, and this p cap is h cross by l, iota del. And you can write this operator in terms of its components. That is px cap will give us h cross by I dou by dou x, and py cap will give us h cross by I dou by dou y, and pz cap will give us h cross by I dou by dou z. And we also have velocity as an observable, and this velocity has the operator v cap, and that operator is h cross by 2. No, it's not 2, it is m I del. And automatically you can write down the components of the velocity. You can write down the operators for separate components of velocity operator.